We're talking about parallel lines and transversals, among other things, but this is where we're going to start. Vocabulary is very important, and oh, by the way, the technology assignment is directly related to this content, so even better. So you can use your notes from tonight as a resource, and you should be able to kind of plow right through it. It does not involve GeoGebra; it involves Desmos, but not the same features in Desmos that are kind of consistent with GeoGebra. I'll show you what that looks like later, because right now I'm just kind of talking, I guess, for the sake of talking. Yes, I do have my pen. Excellent. So parallel symbol, two parallel lines. That's the symbol. All right. So just try not to make them look like an 11, and you're fine. All right. Most people put them on kind of a little bit of a slant, but anything that looks like that is going to be okay. Parallel lines are what are known as coplanar lines. They don't intersect. Coplanar is just, sometimes I think geometry concepts, math in general, kind of goes out of its way to sound more complicated than it needs to be. These are two lines that are on, or lines, not necessarily just two, lines that are on the same plane. All right. So I just kind of look at it like, I mean, you have really, in any given moment, multiple examples of what that looks like. You know, look down, look up, look backwards, look forwards, look left, look right. You see coplanar lines pretty much everywhere. All right. So every surface that you see can be thought of as a plane, and every line along those planes, so each one of these lines, all right, those would all be coplanar, all right, because they're on the same plane. All right, the little crevices between tiles on the floor, all right, the grout between the cinder blocks, which may or may not have insulation, debatable, and if it did, it's the kind of insulation that you don't want to disturb, because you let sleeping dogs lie, lest we all die. So asbestos is terrible, and so with the older buildings, it sometimes finds its way in there. So I'm kind of rooting for there not to be any insulation in here, because if it is, it's probably of the asbestos variety. But anyway, these really any of these lines would be considered coplanar. All right. Parallel lines are ones that don't intersect, right? So they're lines in the same plane that don't intersect. So if you just follow any one of these channels along the ceiling, along the walls, along the floor, you're finding examples all around you of parallel lines in a plane. All right? Parallel planes are planes that don't intersect. Right? So that ceiling makes up a plane, so does the floor. They're parallel to one another. They're what we call equidistant from one another. Right? The distance between ceiling and floor over here is the same as the distance from ceiling to floor over there. Right? Maybe differs by a smidge. Mathematically, we would say that they have to be precisely the same, but we know practically speaking that's, virtually impossible. Right? So you got to deal with the curvature of the Earth. So that in and of itself poses a problem. Also, gravity. We rely on gravity to establish horizontal for us. So I don't know. Everybody comes from different backgrounds. I don't know how many people have experience with construction in any way, but I'm willing to bet whether you've seen it live or you've seen it in a movie, you've probably seen cement being poured into a form. Whether it's like a mafia movie where the cement's being poured and the dude's being thrown in there with it. There's that. Or just, driving down the street, you see the workers that are making a sidewalk. Right? They're pouring the cement into the form. That's what the cement will take the shape of once it solidifies. But those opposite sides are going to be parallel to one another. But that surface is going to be horizontal because gravity is going to allow it to set in a horizontal fashion. All right? And so anything that's parallel to that would also be horizontal. That's what we would define as horizontal. My mom lives in a, I guess it's like 300 years old now. When she bought it, it was like 275 years old, but that was like 25 years ago, ish. Yeah, everything had like settled, so nothing was level. But you can level out a floor pretty easily. You just use, well, it's, I mean, some of the brands just call it leveler. You know, it's a type of loose cement that you just pour onto the floor wherever the low point is, and just let it set, and it actually creates a horizontal surface, right? So you're letting gravity kind of level it out, right? That's part of the applications of a lot of this stuff that we're going to talk about. Because honestly, you look at this and you say parallel lines, parallel planes, transversal skew lines. It's like, okay, cool, we're learning about shapes and stuff. Sounds great. What could it possibly be used for? I just showed you a bunch of examples. I mean, this is an antiquated building, but you know, it's still standing. So there's got to be some merit to the way it was constructed, right? So these properties and characteristics come into play pretty significantly. All right, skew lines, lines that don't intersect and are not coplanar. So those are kind of interesting to think about. They're not coplanar, which means that they're living in a different plane, but they're not going to intersect either, right? So you're kind of looking at, for example, a plane, a line that's living in this plane compared to a line that's living in that plane. They could run parallel to one another. They could maybe not run parallel to one another. Maybe one of them's running that way and one of them's running that way, but they'll never intersect because they're not living in the same plane. I kind of equate that to air traffic. You know, if you were to say that a plane is going to go in the I don't even know if this is west, but I'm going to say western direction, and another plane is going to start off in the southern direction and go north. You might say collision, but there's a lot of variables that come into play. At what time will this plane pass the line that this plane would be traveling through, and at what altitude would they be flying at? All right. So if you looked at a top view, you might see two planes that are kind of on a collision course, but one of them's 300 feet, 10,000 feet above the other. You know, all sorts of different possibilities. They're living in a different plane. All right. So these are some things that you can consider in the real world that, you know, like, again, looking at the vocabulary words, you know, in an academic sense, yeah, I'll get it right on a test, I guess, but, you know, it's what you can take away that's most important. Transversal is a line that intersects two or more coplanar lines at different points. All right, so the line's got to live in a plane, and you have to have a third line that's going to intersect those other two lines. We call that a transversal. All right, so that's what we're going to focus on, at least for now. That line that's labeled T is the one that we're going to refer to as the transversal. All right, it's the one that intersects two other lines. All right, and when you have a transversal passing through two other lines, it forms a bunch of different angles. All right, so what we get are angles that we're going to have to define. Some are going to be, you know, obvious in terms of their relationship, and some maybe not so much. All right, so we have exterior angles. I think those are easy to identify, especially when you see the definition. Angles that are outside the two lines. So I'm going to highlight my two lines. Let me make that a little thinner, if I can. That one's fine. These are the two lines in question. I need all the angles that are outside of those two lines. And you're like, what does it mean to be outside? Exactly what it sounds like. So between the two lines would be inside, beyond the two lines would be outside. So the angles that would fall into this category would be 1, 2, 7, and 8. Interior angles, 3, 4, 5, and 6. right? Consecutive interior angles. Those are, you start getting into some fancier terminology. Sometimes they give you a clue as to what the definition is. I like the terms that kind of give you a sense of what they mean just by being the term themselves. Consecutive interior angles, I don't think are necessarily, I don't think that's that kind of term. I don't think just seeing the word consecutive makes you think that angle 3 and angle 5 are going to be consecutive interior, and so will angle 4 and angle 6. But the definition is what's going to allow us to make that determination. All right. Angles in between the two lines on the same side of the transversal. All right. Honestly, most of the time when I'm studying, I usually, I would say most of that. I'd say 99 times out of 100, I tend to remember the definition of something not by what it is, but what it isn't. All right, so maybe I don't know what a consecutive interior angle is, but I know what an alternate interior angle is, and I know what an alternate exterior angle is. And so consecutive must not be that. And by using that knowledge, I'm able to kind of put it all together. So alternate is going to be on opposite sides of the transversal. So they're alternating, one on one side, one on the other. So for exterior, we're talking 1 and 8 as an alternate exterior pair. And then 2 and 7. For the interiors, we're talking 3 and 6. And angle 4 and angle 5. Specifically those pairs. Like for exterior and interior angles, it was just 1, 2, 7, and 8, just 3, 4, 5, and 6. But when it comes to the consecutive, alternate, and so on, it's the pairs, 3 and 5. That's one pair of consecutive interior angles. 4 and 6 is another pair, right? They go together. Any other mixing and matching would be incorrect. Corresponding angles, right? Same position, but in a different angle cluster, right? So you got the cluster of angles. I'll use my highlighter again. I got a cluster up here, and I got a cluster down here. If it occupies the same position, but in a different cluster, then they're corresponding, all right? So, for example, and there's a lot, so I'm not going to write them all, but for example, I would say angles 1 and angle 5. I could say angle 2 and angle 6. But I could say, like I said, I could say a lot more. All right, there's a total of 4 sets of corresponding angles. I don't want to have to write them all. All right. All right. Vertical angles are the pairs of opposite angles made by 2 intersecting lines. I would say the name vertical angles is probably one of the more frustrating names, because like consecutive interior angles, you can kind of convince yourself somewhere along the lines that, okay, 3 and 5, yeah, it's one after the other on the same, okay, maybe that's what consecutive means. But vertical angle, there's nothing vertical about vertical angles. Right? So I'm going to just kind of pull a angle cluster off on the side here. That was supposed to auto-correct into a straight line. And there it is. So I have 1, 2, 3, and 4, for example. All right, so this, I'm redrawing over here. All right, you have an intersection between 2 lines, creates 4 angles. The ones that are opposite of one another, those would be the vertical angles. All right, so we have multiple sets of vertical angles. So in this case, I'm looking at angle 1 and angle 4. I could also say angle 2 and angle 3. But just like the other case, there's a couple more. I could say 5 and 8, and also 6 and 7. All right. So, you know, the names themselves, some of them are a little easier to identify than others just based off the name. But, you know, having access to good notes is going to be a kind of an important piece here because, like I said, some of these terms, they just do nothing in terms of helping you understand what they are just based off the name. Right? So, like if I were to tell you that, like a term, intersecting lines, just based off of the concept of the intersect part, you can figure out what that term means. Vertical angles, you're not getting that. You're not, there's nothing about vertical angles that's telling you the relationship that I just showed you. All right. And so, right into the fire, I guess. Not really. You're not asked to identify any angles, but it says identify the sets of lines to which each line is a transversal. All right. So again, a transversal is defined as a line that intersects two other lines. All right. So basically, all I'm asked to do, and I'll just make a note of it at least this first time, is identify two lines. So find two lines that A intersects. All right, so find two lines that A intersects, just based off the diagram. So you're just following the pathway. And it seems to intersect with C and F, yeah. All right, so for B, it's the same idea, just with line B. All right, now it could be more than two lines, but really we only need to identify two lines. All right, because in the case of C, it looks like it's going to intersect. Yeah. Where is C is? Oh, I'm sorry, B. I meant to say B, but C, F, E, and even D. But if you want the cleanest ones, you could say definitely C, and you know pick whichever one you want. You can't go wrong. I would probably lean towards F or E. But you could even make a case for C and D. Now, that last little one, you might want to shy away from it just because there's no guarantee that D goes directly through that intersection, but it really doesn't have to as long as it crosses B somewhere. You know, so it accomplishes the goal. All right. So, what about C? Where is C going to cross? B and A. B and A are the definite obvious ones. Yeah. Also D. D and F. And even E. So oddly, my hesitation was putting those letters in alphabetical order. Weird. Yeah, it's weird because you might look at this and say, well, it's not gonna cross E, for example. But I mean, the arrows are there for a reason. If you follow this to its logical conclusion and follow this one, eventually they will intersect. Right? So that would make it a natural intersection. just because it's not happening in the actual diagram, if the arrows are there, it could happen. So for something like this, if I gave it as part of an assessment, you got to kind of imagine that it's in the middle of a giant sheet of poster board, and that you have a big T-square, and you're just drawing those lines as far as you can in every direction, and seeing what happens once you do that. All right? That's actually a great idea. I might do that. D definitely is going to intersect what and what? The obvious ones.
C.
Definitely is going to intersect C and B. But if you extend it further, we could also say that it's going to intersect with F and E. All right. Now, again, just like the other problem, I could extend it backwards, which would mean that it's actually at some point going to intersect with A. All right. So basically, anything that we know is not parallel is going to intersect in subcapacity. It's just a question of whether it's going to be a meaningful intersection or a useful one or the most obvious one. All right. Now, since this problem didn't give us any information about angles or lengths of sides and stuff like that, it's all academic. It didn't matter which ones we selected. But, you can make a case for lots of different things. That's the whole point. So numbers 2 and 3 are talking about classification. So I'll just do one of them because they could take a little while. But I also want to emphasize certain attributes because, and this is going to, like I said before, tie together in with the tech assignment. So when I'm looking at 4 and 5, what I like to do, and this is a pretty standard approach that most people use, is when you're talking about a particular pair of angles, what we do is we mark them off using little arcs. If you know that they're congruent to one another, we give them the same arc. If we know that they're not congruent, and for whatever reason I can't draw an arc right now, if you know they're not congruent, we give them a different number of arcs, right? So the question might be, well, okay, how did we know 4 and 5 were not congruent to one another? Well, one's acute and one's obtuse. Visually, they're not going to be congruent to one another, right? So, but they didn't ask us about that.
What's the password for the computer?
Right. So, yeah, you can make a determination based off visual observation, and also just bear in mind, protractors are a useful tool. I remember telling my students when I first started teaching in the high school, when they would take Regents exams, I think I might have told you this already. If I didn't, then I should have. If I did, I apologize for repeating the story. But I would tell them, you can't just measure the angles on the test. The question will say something like, find the measure of angle C. And it'd be like, and it would be a multiple choice question. Like, you can't just measure the angle. You have to do the algebra and solve for the missing angle. And they accepted it, because, especially since in the diagram it said not drawn to scale. A few years later, I found out that all the diagrams were drawn to scale and that you could measure them. And so for a multiple choice question, to not have to do the algebra and only to take a protractor out and use that to determine the angle, I mean, that's like a deal breaker. I mean, it's like you can get stuff right without knowing math. This is great. Although some would argue that you're learning the more important skill by using the protractor. Like, how often are you going to solve algebraic problems? I mean, they show those, like, you look online, they have those T-shirts that say, "Yep, another day as an adult, and I still haven't used algebra yet." But so that's true for a lot of people. The reality is, what are you more likely to do? Are you more likely to measure in some way, or solve an algebraic equation in your adult life. Measurement is probably more of a likelihood. All right, so what's the skill that you should probably get more comfortable with? The idea of measurement. All right, so this question didn't ask us to determine congruence, but the first thing I would consider doing if I was asked to determine whether 4 and 5 are congruent to one another, and they look close enough, I'd slap a protractor on there and see. You know, there's nothing wrong with that. Measuring, that's why we went over that. Okay? So in this case, they're just asking us to name them. They're in between two transversals. Now we got transversals all over the place here, but the two transversals that are relevant are these guys. I shouldn't really overdo that because I'm going to cover everything up. And so 4 and 5 would be consecutive interior angles. All right. Later on in the lesson, we're going to learn that if those two lines are parallel to one another, there is a relationship between consecutive interior angles. Okay, so it'll be a useful relationship. But it's something that, like, let's say you forget it. In the moment of truth, you forget it. Slap a protractor on there. You'll be able to see what that relationship is. All right. 7 and 9. I'm looking at 7 here. Let me get it in there pretty good. Really, undo has to do with zoom too? Jeez, that's not what I had in mind. So I'm just gonna put 3 rings on this one because I don't know if it's congruent to either of the other 2 angles. Well, actually, that's not true. I didn't think that through. It's definitely congruent to 5 because they're vertical angles. But they're asking us for the relationship between 7 and 9. They're alternate. Well, interior, yeah. Because these would be the 2 relevant parallel lines. And actually, as it turns out, they're congruent. Again, they're not asking us, but, you know, while we're here, we might as well at least consider it. So alternate interior angles. So then we get into 5 and 12. I'll bring it in again. Same set of parallel lines. Well, actually, we don't know that they're parallel. Same set of lines that are cut by this transversal. These 2 angles, 5 and 12, are outside. All right, they're outside of that transversal, and they're on opposite sides of the transversal. So we're going to say they're alternate exterior.
So exterior would be pertaining to the lines that are transverse.
Yeah, so you're looking at the 2 lines that are getting cut by the transversal. Any angles that are outside of that, those 2 lines are the exterior ones. All right, and so then we're looking at 2 and 4, which brings us way back up to that top cluster of angles. And those angles are opposite sides of a cluster of angles that are created by the intersection of 2 lines. That's the definition of vertical angles. All right, and so if I knew some key facts here, I'd be able to make a lot of conclusions. Vertical angles are always going to be congruent to one another. All right, and we'll get to that in more detail later on. So if you have a cluster of angles that are created by the intersection of 2 lines, the vertical angles, so the angles opposite each other in that cluster, are always going to be congruent to one another. All right, so I know 2, 4, 5, 7, 9, and 12 are going to be congruent, but also 1, 3, 6, 8, and 10, 11. All right, all congruent to one another, just because they're vertical angles. Alternate interior angles and exterior angles are often congruent to one another, but it depends on the relationship between the two lines that are being cut by that transversal. All right, if those two lines are parallel to one another, then alternate interior angles are going to be congruent, and also alternate exterior angles are going to be congruent, but only if those two lines are parallel. They look maybe like they could be parallel, but also depending on the angle that you look at it, it looks like maybe these two are a little bit closer than these two. Maybe they're exactly the same, and you know, my mind's playing tricks on us. But unless it's explicitly stated in the problem, we can't assume that the lines are going to be parallel to one another. All right, so that's got to be a given piece of information. All right, so I'm going to skip number 3 because that's like beating a dead horse, which is just terrible. Leave the horse alone. But I'll put a star on it so that you can tackle it on your own for homework. And now we're going to get into what I was just talking about, the idea of parallel lines and transversals. And this is the connection, or one of the many connections in geometry between, you know, all the shapes and measurements and things like that, and logic. All right, because what we're looking at are conditional sentences here in each case. And those sentences are true, but they lead us to other sentences that are also true based on the laws of logic, all right, which we'll get to in a sec. But we'll start off with the first one. If two parallel lines are cut by a transversal, all right, so I have two parallel lines. It's given that these two lines are parallel. They're cut by a transversal that we're calling T. Then each pair of corresponding angles are congruent. All right, so quick example. Again, with corresponding angles, alternate interior angles, stuff like that, it can be a little daunting to have to write out every possible way in which this could be satisfied. So I'll just do an example or two. We could say, for instance, that angle 1 is congruent to angle 5. All right. Corresponding angles, again, are angles that hold the same position within different clusters. All right, so I got my two clusters here. I got this cluster right up here, and this cluster right down here. What I'm saying, based off of this first relationship, is, for example, angles 1 and 5 are congruent to one another. All right, but there's other possibilities, like angle 2 and angle 6. Poor quality congruent symbol. Also 3 and 7, also 4 and 8. All right, so a lot to write, but I think most, you know, historically most people have gotten the idea after a couple of examples. Oh, that's a hell of an arc. Sorry, I just gotta at least try to make it look halfway decent. Yuck. Whatever. All right, two parallel lines are cut by a transversal, then each pair of alternate interior angles are congruent. Fortunately, in this case, there's only two possible pairings. We're looking at angle 3 and angle 6 being congruent. And also 4 and 5. All right, so angle 3 is congruent to angle 6, and angle 4 and angle 5 are also congruent. Oh, yoy. The alternate exterior angles will be congruent. So we're talking 1 and 8. Two and 7. As it turns out, every angle that I indicated with 2 arcs, with a double arc, they're all going to be congruent to one another for one reason or another, whether it's alternate interior angles, alternate exterior angles, vertical angles being congruent, lots of different possibilities. Bottom line is all of those double arced angles are going to be congruent, all the single arced angles are going to be congruent to one another. All right. If 2 parallel lines are cut by a transversal, then each pair of consecutive interior angles are supplementary. All right, so that's the first weird one. All right, supplementary. When you talk about supplementary angles, you're talking about 2 angles. Well, really, I mean, they don't have to be just 2 angles, but angles whose sum is 180 degrees. All right. What this is telling us is that each pair of consecutive interior angles is going to add to equal 180 degrees. So if I take the measure of angle 3 and add to it the measure of angle 5, I'm going to get 180. But also 4 and 6. The same is actually true for the the consecutive exterior angles, but it's the kind of thing that it's not really easy to quantify. Well, quantifying it is probably the easiest part. It's difficult to find the application of something like that, because if I tell you that we're going to call 1 and 7 consecutive exterior angles, you'll be like, I get the consecutive part, but I get the exterior part, but where are you getting consecutive? They're nowhere near each other. If we're defining consecutive as being on the same side of the transversal, then that's justified. But I don't include that for 2 reasons. One, because I forgot to put it in there. I forgot to create a row that said consecutive exterior angles. And so now I'm just doubling down on that error by saying, you know what, we really didn't need it anyway, because if I know, for example, that 1 and 4 are congruent to one another because they're vertical angles, and I know 6 and 7 are congruent to one another by vertical angles, these 2 guys, 4 and 6, they're going to add up to 180. Because 1 and 7 are congruent to 4 and 6, they also have to add to 180. All right, it's just direct substitution. All right, so my error made a talking point at a minimum. But we'll get into what that looks like in terms of the notation in a little bit, because it warrants more than just sideboard work, and I don't want to just leave it at hand waving. So you get it, right? So we'll discuss that a little bit in more detail later on, but there is a benefit to kind of trimming down a little bit of the notation terminology for the sake of just mastering the stuff that is most useful. All right. Last one, in a plane, if a line is perpendicular to one of 2 parallel lines and is perpendicular to the other, that's just, it's really the kind of thing where you look at it and say, yeah, I guess, yeah, sure. Here's a picture of it. The line is perpendicular to one of 2 parallel lines. All right, so it's perpendicular to N. L and N are perpendicular. And then N is parallel to N. So then L is perpendicular to M also. It's not the kind of thing you'd ever feel the need to articulate. It's just the kind of thing that the brain immediately accepts without question. You're like, yeah, of course. But wait, I gotta prove that? Why do I have to prove that? It's obvious. You know, it's kind of like, why do I have to prove that this figure is a square? Bless you. My brain is telling me that that figure is a square. Why? Because it's a square. You know, why is that a circle? Because it's a friggin' circle, that's why. You know, this falls into that category. But when you kind of look at it in terms of the, you know, the nuts and bolts of it, there is something to be said for being able to articulate the thinking. So we have L is perpendicular, upside down T is a symbol for perpendicular, to N. Right? And we have M being parallel to N. So the conclusion from that is that L is going to be perpendicular also to M. So it really just becomes a logic sentence. So if the first two components are true, then the last one would result because of the first two. All right? Now, if you go the other way, you can kind of look at it, you know, so, or you might look at it and say, L is perpendicular to N, and L is perpendicular to M. So we can conclude from that, so I'll say therefore this time, M is parallel to N. All right, so that's a little consequence of that relationship, is that if you know that a line is perpendicular to two other lines, then those two other lines would have to be parallel to one another. All right, we're going to prove that later on, but it's a nice one to know, because if you ever have to prove a parallel relationship, that's probably the way that you're going to do it. Well, or at least it's one of the ways that you would consider doing it. I used to love/hate questions like numbers 1 and 2, depending on my teacher. It really, for this kind of material, it always came down to the teacher, because it was just a matter of, okay, I'm going to get it very quickly, very easily based on the relationships. And I'll show you how you're going to get it very quickly and easily. But if you have to do like 20 problems like this, it gets old very, very quickly. And so one of my teachers back in the day was the kind that's like, stop doing it once you get it. You get it after 2 problems, you're done with your homework. You don't get it until after the 18th problem, keep doing the homework. Other teachers were like, all right, you got to turn in all your homework tomorrow. And for those classes, I did well on the tests, but I did not do well in the homework category. They're like, yeah, so your grade is this. Just so you know, you're missing 17 homework assignments. And I'm like, yeah, that's because you assigned like 3 hours every night. That is not my thing, right? So if you're, you know, we're a month into the course already. If you're noticing the absence of outside of the classroom work, there's a reason for that. You know, I wouldn't do it, so I don't expect too many people to do it. All right, so they tell us that the measure of angle L is 51 degrees. We need to find specifically measure of angle 10 and 16. Now, the good thing about this kind of problem is it's not asking you to name anything. You know, it's not asking you to prove anything. It's just asking you to figure out those particular values. So, and even better, in this relationship, if you kind of pieced it together as we were going through it, if the angles look like they're the same, they're the same. If they don't, they're not. All right, so when I'm looking at the 3 angles in question, well, one of them is given, the angle 11 is 51. I need angle 10. It looks much bigger than angle 11 versus angle 16, which looks like it's about the same size as angle 11. So I know the measure of angle 16 is going to be 51 degrees. Now, if you look back at everything that we filled out in that table, it really just boiled down to congruent or supplementary. Right? If two angles aren't congruent, they're supplements of one another. So the measure of angle 10 is going to be 180 degrees minus 51, which is going to be 129 degrees. All right, and so little vocabulary term here, note angle 10 and 11, for example. There's many other instances of this, but angles 10 and 11 form what we call a linear pair. Now, a lot of the terms that we'll talk about define themselves. Vertical angles is not one of those things. I think linear pair is. I think it's one of those types of types of terms or terminology in the course that actually tells you a little bit about what it is. Right? We're talking about two angles, a pair, that are linear. They form a line. Right? So if you're starting off at, going off in this direction, you travel 51 degrees, and then you travel another 129 degrees. The path that you would be creating, if you were to just compose your starting angle and your ending angle, would form that of a straight line. All right? So those two angles put together would form a linear pair. I bring these things up because every time you can kind of make sense of a term, it's one less thing to study. It's one less thing to have to look up, scramble to look up when you're working on an assessment. It's just, oh, that makes sense. All right, transversal, I don't know. I mean, transverse, traverse, travel a distance. If you can kind of make a relationship between your own knowledge and the terminology, it becomes a lot easier. You don't have to look things up. All right. Number 2 is pretty much the same thing. So angle 18 right there does not look anything like angle 19, so I know those are supplements, but it looks just like angle 25. All right, so the measure of angle 19 is going to be $1.80 minus 42, so 138. And the measure of angle 25 is equal to 42. Now, the fact that angle 18 and 25 are alternate exterior angles, very useful information. Not for this problem, though. That's the thing. Pick and choose your battles. Eventually, you're going to have to be able to reference that information, but for this problem, if they look alike, they are. If they don't, they're not. And snag this relationship here. Copy, I guess, but then trash it. These problems are kind of fun. I guess we all define fun differently. I just kind of look at any math problem that looks more like a puzzle than a traditional math problem. That's like math fun to me. Like you get down to something like number 5 and it's got X's and Y's in it. You're like, oh, back to algebra. That's not fun. I mean, algebra can be fun in some circumstances, but this is more puzzly than anything else, and that's probably for the best. if you can kind of convince yourself it's more of a brain teaser than a math problem, then you're probably ahead of the game. So what we have here are two different transversals. Incomplete though, right? And so, and I say incomplete because it doesn't extend forever, right? This has a finite endpoint. So I'm not going to be able to travel through this point and extend my line like that earlier problem. I can't do that. This one actually comes to a halt right here. This transversal comes to a halt also at the same location. So you look at this and say, well, how am I going to get my alternate interior angles and stuff like that? The answer is you will, you just got to kind of look at things a little bit differently. I'm looking for angle RTV, which is this vertex angle in here at T. So if I follow the pathway from R to T to V, that creates this interior angle. That's what I'm looking for. Okay, and so I can handle this a bunch of different ways, but I think the easiest way to do it would be to think, well, I was going to say think outside the lines, but that's the exact opposite of what you want to do. You want to think inside the lines. Like literally. Let me just make my pen a little thicker. And that ought to do it. Now this is a relationship that I didn't write down anywhere. And, you know, at some point, you know, at a few points throughout the course, we'll reference this. But I think personally it falls in the category of common sense. If two lines are parallel to a third line, then that third line is parallel to each of the two original lines. Right? So I'm creating a new line here that I know is parallel to the first line, the two original, I'll just keep that short. It's parallel to the two original given parallel lines. All right, just drew it in there. Why? Because now I have a transversal situation. All right, because I can use my alternate interior angle knowledge here. If I had two parallel lines cut by a transversal, I know my alternate interior angles are going to be congruent. So I know that this guy's going to be 60 degrees. And the same would hold true on the other side. Two parallel lines, these two. Well, let me just draw it in a relevant place. Cut by a transversal, the alternate interior angles are going to be congruent. There's other ways to do it, but that's a pretty solid way. So now I just got to add them up. So it would be 60 plus 65, so 125 degrees. Ooh, too thick now. All right. Alternate interior angles, they're very easy to identify, even in a complicated diagram, because generally you're looking at a Z shape. Well, this is how I remember it. Whatever the angle is contained within the Z, those two angles, those would be my alternate interior angles. All right? But you might look at this and say, well, the blue one's not a Z. Well, okay, well, it's the backwards Z. It's the same idea though. Right? So Z or a backward Z, it all has to do with the orientation of your transversal in relation to the parallel lines. All right, so a little Z action go backward Z, but those angles are going to be congruent to one another. Right? So if you could find a Z shape within your diagram in such a way that those two line segments that are opposite of one another are in fact parallel. So that has to be a given. They have to be parallel to one another. Right? Either they have to be stated as parallel or you have to make that determination on your own in some way. But if you can conclude that they're parallel to one another, then those little angles that are contained within the Z, those are going to be congruent to one another. Right? So even this really complicated looking diagram in numbers 3 and 4, they're a lot simpler now. All right, so I'll show you another way to do it in a minute. Let me just reproduce the diagram. Alright, so a little Z action here. And a little Z action right here. Alright, so this is going to be 45. And this will be 48. And so, since I'm looking for, and honestly I didn't even read the instructions, I'm assuming we're looking for this angle. If not, then I'm just going to change the problem anyway. 48 degrees plus 45, going to be 93. IGE, yep. Measure of angle IGE is in fact 93 degrees. All right. Now, I don't want to stifle any creativity here. You know, just because I chose to do it that way doesn't mean that that's the only way to do it. And in fact, that'll be a good part of geometry, but it's also going to be an incredibly frustrating part of geometry. And what I mean by that is, and it's just from experience over the years, especially in the high school class, what I do is I give them a worksheet, you know, a little instruction, and give them a worksheet with a bunch of problems on it. Post my answer keys online, tell them check their answers against the key if they need to, and they do. And then they look at their work, compare it to my answer key, and then immediately get out one of those jumbo erasers and start erasing all their work. All right? High school freshmen, you know, they don't always think this stuff through, at least not yet. I'm still working on them. What I am working on mostly is getting them to watch my videos. So I figure every time I talk smash, you know what I'm thinking? Like it's Ash Wednesday, and so I've been craving, you know, because like you don't crave burgers all the time, except on a day that you can't have one. And so, like I wanted a smash burger.
Shake Shack is better.
Shake Shack is better.
Mm-hmm.
It is, but I passed Smash Burger on the way here, so that's what was in my mind. Yeah. And Sister Nora texted me this morning telling me not to eat meat as I was walking out of the house with a big Italian combo in my bag along with beef stew, you know. Sister Nora is the mother-in-law. That's how I refer to her. Because I don't know if she does it on purpose, but she, I think, waits until she knows that I'm at the point of no return Like, yeah, I'm gonna get him now. He's gonna totally eat meat today. Now I'm gonna send him the reminder. Like most of the time, it would be like as I'm walking out of Dunkin' Donuts with a sausage, egg, and cheese. Like, it's never walking in, and it's never like the night before. You know, like when I'm preparing my lunch for the next day.
She's watching you.
I think so.
They have to be on the
Yeah.
alternative. I'm not
Yeah, I
sure.
know.
I don't trust that. I don't know what it is.
Well, there's two things. One, I tried whatever the Costco version of it is. I tried that one, and it was all right. It was not meat.
Right.
You know, like I think it was part of a burrito, and it was like I get what you're doing here. You're just burying it in other things, so that you could hide the fact that it's not meat. They're counting on the texture of it being enough. And somebody said that they thought the Impossible Whopper, I think is what it's called at Burger King, is they said it tastes just like the regular Whopper, which to me is an indictment on the regular Whopper. Because if you can just, like, using science, manufacture a cheeseburger that is indistinguishable from the real thing, then what was the problem with the real thing to begin with? Like, you couldn't taste it. And the person who tried it was like, well, it's buried in so many other things, like the lettuce, all that stuff, that you can't even notice the meat to begin with, right? I'm anti-Burger King. I'm really getting into this right now, but if you, and I'm very passionate about it. If you, I don't know if the website is still up, but if you're on the fence, if you're like, I don't know if I should be doing Burger King or stuff like that anymore, go to burgerkingbrokemytooth.blogspot.com. If that website still exists, you'll see a posting from me, because one time, and the last time I had a burger from Burger King, I was driving my wife to the airport, went through the drive-through, got what I wanted, get on 287. And I took a nice big bite out of it. And, you know, I was aggressive because I was hungry. So it was a big, hard bite out of the burger. And I heard a crack in the back of my mouth and felt it also. And I was like, what the hell was that? So there was a bone in the burger. And, yeah, I tried to. They wouldn't let me. They said I couldn't prove it. So here's the issue when it comes to trying to litigate that sort of thing. You need to prove the chain of custody. So I had to prove that that bone was from that burger from that restaurant. It's impossible. There's no way. The only way that you could actually prove that, and even this is a little iffy, is if you get the burger when you purchase it at the counter, open it up, take a big bite out of it, crack a tooth right then and there, and then say, hey, listen, we got a problem, Houston. So, like, basically, there's no way they could ever get in trouble ever. So I was like, okay, so that rules out Burger King definitely, but how would McDonald's, Wendy's, or anybody else be any different? So you hear the stories all the time about how somebody buys a Subway sandwich, and then there's like some horrible thing in it, and it's like you can't even prove that it came from that restaurant. They're like, I have a receipt. Well, how do we know you didn't pay for it at some other restaurant, eat it, throw away that receipt, and then buy a sandwich from this one, get a perfectly fine sandwich, and keep that receipt? You're framing us. There's no way. There's no way. So, just don't do it. The clear and obvious answer is buy a farm and produce all your own stuff. But that's not possible. So, like, taxes around here are outrageous. And I don't even know the first thing about farms. Yeah, upstate. That's the answer. Like, just leave this area. I looked into the prices for inflatable wraps in order to put it out in front of Burger King. It is prohibitively expensive. You can't just be like, oh, I'll rent the inflatable rat for a day, and get it for like $100 or something like that. It costs a ton of money. You can't like, it's horrible. Freaking Burger King.
So do you hesitate into biting into sandwiches now?
Every single time.
Small bite, small bite.
Sometimes you're just so hungry.
I have a patient. I work for an oral surgeon. And yesterday he came in and he hands me a paper for workman's comp. And I'm going, workman's comp for a tooth? He was on a phone conference eating a chicken quesadilla, bit the bone, and it broke his tooth and went through his tongue. So he's going through workman's comp.
When you get the cake?
I don't know.
Yeah,
So
'cause-
why are you on a conference call while eating lunch? That's your problem, not their problem.
Yeah.
But it's
What?
the same thing.
I wish I knew that, because I bit a hole in my tongue once because I was eating a salad while having a conversation with somebody, and I forget what the word was that made it all happen, but it was like consequence or something like that. But for whatever reason, like I was taking a bite, was talking. This is why you don't talk with your mouth full, and it just came down. I got a pretty sharp incisor. Just came right down in the middle of the tongue. And I was like, oh, that really hurt. And I thought it would be all right, because I bite my tongue repeatedly, unfortunately, and my cheek and everything. I bit my tongue on the way to the classroom right before class started. Twix. I was having a Twix. Just bit my tongue. Still hurts. I don't know. I don't know what the deal is. But I had to go to the ER because 7 hours later it was still bleeding.
Oh my God.
So I had to get a shot of epinephrine directly into my tongue. And they're like, if that doesn't work, we'll give you a stitch. And I'm like, well, if you're going to give me a needle now, why don't you put like a little numbing agent in there and stitch this bad boy up right away? And they're like, well, the epinephrine will numb it anyway, so if that does the job, because it'll constrict the blood vessels, if that does the job, we won't have to worry about the stitch. This is at Putnam Hospital. Like, apparently it was a slow night. The entire ER came down to watch this. They're like, we've never seen anything like this before. I had a whole crowd of people watching me take a needle in my tongue. And then after that, I had to eat a turkey sandwich. That was the thing. I couldn't leave unless I could prove that I could eat something without opening the wound again. And I'm like, this is just wonderful. So, I look like a vampire going in there. It's brutal. Oh, undo. All right. Well, I'm going to find out if my freshmen are watching these videos tomorrow. I'll tell you that. So, anyway, a slightly different approach. And it's optional, because if the other approach works perfectly fine for you, you might say, well, why would I do it this way? Okay? But you might say, well, I did not understand that other approach at all, so let me try this way. 48 and whatever this angle is here would form that linear pair I was talking about previously. So these two angles are going to add to equal 180 degrees. All right, so this is going to be 180. Now, it's going to involve a little bit more work, a few more steps, but it's all calculation. It's still not algebra, so, it's kind of a win. All right, so 180 degrees minus 48 is going to be 132 degrees. This angle and this one also form a linear pair. So, same deal, 180 minus 45, though, not 48, in which case I'll get 135 degrees. I know that these two have to be 90. Well, I guess they don't have to be. It's just the way I drew that line is forcing them to be 90. That was the whole point. All right, I created a pentagon out of this. All right, so I know that I'm going to have 90 degrees. 90 degrees. The one thing that makes this slightly more, obviously the computations make it a little bit more challenging, but in terms of the theory behind it, what could make it the kind of approach that you're saying, well, I'm not going to do it this way, is you would have to know how many degrees are in a pentagon. So you'd have to recall content from the last unit. But since we're going the open notes route, it's really just a matter of researching that information. So there are 540 degrees in a pentagon. All right, and just a quick refresher on that, because I kind of feel like it's the sort of thing that I can't go over often enough. The way I know that, I'm just going to draw a quick pentagon. Poor quality, of course. I did not intend it to be that poor. Or that poor. You know what? I'm just gonna use the regular line draw tool, or just regular pen, I mean, and just draw it. And then maybe get rid of all the crappy line segments due to my nerve damage. We know that there's 180 degrees in a triangle. So the way I know that there's 540 degrees in a pentagon is I create as many triangles from a single vertex that I can in any polygon. So I can create a triangle here. So I connect to all the other vertices. So these would be 3 triangles at 180 degrees each. So that's where I get the 540. All right, so if you happen to know it off the top of your head, great. I mean, I didn't know that information off the top of my head till I was a math teacher, specifically a geometry teacher, so it's understandable if you don't, but you could always figure it out is what I'm getting at. All right, so I know that it should total out to 540. Then I can subtract off all the other angles, all the ones that I know. And again, more work, but if your brain takes you in this direction, then it might be necessary work. And so you'd end up with your 93 degrees this way, because we only had the one unknown angle here. So, yeah, you might look at this as New York to New Jersey via China, but you know, it's still a way to do it. Something to keep in mind when we get to proofs, and this goes back to what I was saying about the freshmen before. You know, they see my answer key, they compare it to their work, and they whip out the jumbo eraser, and they start erasing all their stuff. Figure they must have done it wrong, and then I have this conversation with people on a daily basis. They call me over to ask me how to do a problem, and I can still make out what they erased. And so I'd be like, well, you were on the right track. Oh, you just missed a negative sign in your last step. And then my new line is, why did you erase all that? Were you embarrassed? Were you scared? Did you think I was going to judge you? It's fine. Just show me the work so I can see where you went wrong, if you went wrong. Most of the time, they didn't go wrong, you know, or at least not in a significant way. So you see my answer key that has this nice 2 steps and done, and you did all this work, and you're like, well, I must be wrong, so you start erasing it. Reality is you're doing just fine, right? And the reason I'm kind of harping on this is when we start talking about proofs, our brains are all going to take us in different directions. And we're all going to be right? So the pathway that you choose to get you to prove a relationship, in many instances, it's going to be completely different than the approach I choose, but you're going to be just as right. If not, you might even be more right than I am, because you may have chosen a route that is more efficient than the way I went. Quick, I mean, this is, tonight's like story night for some reason, I don't know, but like, this is a quick one. I was teaching a calculus class, like, I think it was 10 years ago. Honestly, forgot how to do the problem. I was working on the board, forgot how to do the problem. So I start upper left-hand corner, stream of consciousness, just anything math like that I could think of that I knew was correct. I was like, all right, and so then we do this, then we do that, then we do that, then we do that, then we do that. Before I knew it, the period was over and I was on that part of the board. So I had worked my way around the entire classroom. And at the end of the class period, one student was like, couldn't you have just done this? It was literally a two-step problem. And it had nothing to do with the work I did. I mean, I got there eventually, but it took me 40 minutes. It took that student like 10 seconds. All right, so we're gonna have those experiences when it comes to proving geometric relationships. Sometimes it'll be me that's going the circuitous route, and sometimes it'll be you, but bottom line is, as long as we get to the destination, it's fine. All right. Honestly, I don't want to do this problem. When I was putting together the notes for this course, I kind of did it with like traditional geometric relationships and things like that. And it's like as I go through it again and again, I start realizing there's certain things that just don't need to be here. So, like algebra, it does have its place. It's just this is kind of like a shoehorn. It does not back really quickly, and we're really not arguing it. I don't think so. Proving lines parallel. So proofs. Vocabulary, important vocabulary. Weird vocabulary. Equidistant. Honestly, I thought my ninth grade teacher had a speech impediment because he kept saying equidistant, and I'm like, can you not say equally distant? It's not, is that like his weird tick or something? Like, no, it's a word, equidistant. Has the same distance. It's kind of strange because it means equally distant. So why can't we just say that? Because some schmo who created geometry decided that this is what we're going to say. You know? It's fine. Locus. So equidistant defines itself. Locus, I mean, it does not. A set of all points that satisfy a given condition. Definition, parallel lines can be described as locus of points in a plane equidistant from a given line. All right, so locus of points, set of points, or a path of points. All right, the loc part of locus, that's talking about location. All right, so really you're talking about location of all points. If you were to take the word location and combine it with focus, you get locus. All right, so you're focusing on location. That's all locus is talking about. All right, loci or loci. There's different ways of saying that one. That's just a plural of locus. All right, so we don't say locuses, but it's really just talking about the path of points that's generated by a certain set of conditions. All right, so if I were to say that you have the locus of points that's equidistant or equally distant from a single point, what I'd be talking about is the path of points that would be created if I went the same distance in every direction from that single point. So every possible direction. What path do you think I'd be creating if I were to connect all of these points? Yeah, it's going to be a circular point. So every time I take a step away from that central point, I would plot a point, a new point, do the same thing in another direction, and another direction, and another direction, and connect all of those, and you end up with a circle. All right, so that's a very simple way of visualizing the concept of locus. And in this case, we're talking about parallel lines. Locus of points equidistant from a given line. So if I have a single line and I want to go, let's say, 6 inches away from that line, but for any point along that line, every time I plot one of those points, I'm going to be along another linear path. And that path will necessarily have to be parallel to the original line. All right? So that's actually the definition of parallel. Parallel is the locus of points equidistant from a given line. But again, it's another instance where we're taking something that we know is just like, it's common sense. And we're trying to make it more than it needs to be, I guess. But there is a rationale, there is a reason for this. Just curious about something. Nah, I really couldn't make those tables wider. It is what it is. Just looks like I had so much room, but it's just the way I have it zoomed. So this is similar enough to the rules on the previous page that you might be like, well, you just copied and pasted. And to some extent I did, but they're different enough that they have their own meaning. If two lines in a plane are cut by a transversal so that the corresponding angles are congruent, then the lines are parallel. All right, so I'm just gonna I'm learning. I'm getting there. Just gonna tuck that in here real quick. It's not letting me. Son of a gun. All right, that's what I'm gonna live with. Or maybe not. That's hilarious. Lock it up. There it is. All right, so the original relationship was if two parallel lines are cut by a transversal, then each pair of corresponding angles are congruent. All right, so if we look at what we have now, it seems as though we've taken the premise. I'll just take the parallel part, and the conclusion, corresponding angles are congruent, and did the old switcheroo. So we switched premise with conclusion. Logically, this is known as the converse. All right. So this is what we're getting from this is that if we can show that the corresponding angles are congruent, and so same parameters. We have two lines, and they're cut by a transversal. Right. So those still have to be in place. But if we can show that the corresponding angles are congruent, then we will have demonstrated that those lines must be parallel. All right. So the reason I'm bringing this up is because we already know all these rules. They were 2 pages ago. All these are is us looking at those rules in a different way. We're using those rules to help prove the parallel relationship from the congruence, rather than using the parallel relationship to determine congruence. All right. So subtle difference, but meaningful. All right, because here we're not making the assumption that the lines are parallel, but if the angles are congruent to one another, then we can conclude that the lines are parallel. All right, so I don't think I need the examples here because they would just be the same things. Yeah, so I'll take that as a typo. Yeah, because all of these, none of these require examples because they would be exactly the same as the previous set of examples, and I don't want to make you write them all over again. All right. If a given line on a point in space, then there exists exactly one line through the point that's parallel to the given line. All right. So that's this diagram here for some reason, and it actually should be swapped. But it's not. But I'll take that as a typo too. All this rule is telling us, and I'll just write C above. Is that if I have a line and a point in space, there's only one way that I can draw a line through that point that's parallel to the given line. Kinda.
So then wait, what if that point was placed, let's say, like very closely to O? Is that O? Yeah.
Yeah, it would be a different line,
Oh.
but it would still be the only line that could exist. And that's a good point, because even if it was if it was placed directly on O, you would still have a new line. It would just be the same line as O. All right? So it's kind of weird to think that you could have two lines occupying the same place at the same time, but there's really nothing wrong with that. All right? Shortest distance between a line and a point not on a line is the length of the segment perpendicular to the line from the point. That's a mouthful, but all that's saying is if I wanted to find the distance between these two lines, then all I would do is find that perpendicular distance. All right, this would be the shortest distance. It's a real life relationship that people say it all the time. Shortest distance between 2 points is a straight line. It's an oversimplification of the idea, because it really depends on where those 2 points are. I mean, that would be true, but that might not be the most meaningful piece of information. If I have two lines that I know are parallel to one another, and I wanted to find the distance between them, yeah, the shortest distance between 2 points is a straight line, but I don't think this is going to be the most useful set of 2 points. If I find that distance, I'm not finding the distance between those two lines. Right? That's not the shortest distance between the lines themselves. What I would want to do is find two corresponding points between the two lines and find the length of that segment. But in order for that to work, they need to be perpendicular to the lines themselves. And that goes back to the rule that we were talking about before, and that is if a line is perpendicular to one of two parallel lines, it is necessarily perpendicular to the other one. Sorry, that was a little off. I'm just cleaning it up. Kind of. All right. In a plane, if two lines are equidistant from a third line, then the two lines are parallel to each other. I mentioned that one before, but like I said, that one falls in the category of common sense. All right. But you see examples of that all the time too. You know, you're driving down the road, you see the two lines that make up the shoulder, and then you see the double yellow line in the middle. They're all parallel to one another. They're following the same path. They're not going to intersect. And the other one I talked about also. If two lines are perpendicular to the same line, then they're parallel to one another. Right. So really, I didn't need this example column at all. So I'll take that as a typo. All right. So the example below is just determine which lines, if any, are parallel. Right. So the only way that we're going to be able to make the determination of parallel is, well, the only way. The only way is to force one of these or more than one of these rules into this situation, or force this situation to fit one of these or more than one of these rules. All right? So I would be looking for things like alternate interior angles. I would be looking for any kind of obvious statements in terms of perpendicular lines and stuff like that. All right? So I'll start off with just identifying all the angles, because we could do that. I know the vertical angles are going to be congruent, so this one's going to be 77. I know any linear pair is going to add up to 180 degrees. So any two angles that when you put them together form a straight line are going to add to 180. Right? That happens in a few different places. It happens here, it happens here, it happens here, happens here. Okay, so it happens everywhere. All right, so this guy right here is going to be 180 minus 103. That's 77. All right. So as it turns out, that angle only really needs one arc because that's going to be congruent to this 77. So I only distinguish them with different amounts of arcs if I know they're not going to be congruent. All right. These two angles have to add to 180. These two have to add to 180. These two have to, so they all have to add up to 180. Pretty much. So this one looks like it's going to be obtuse. It's going to be the result of the calculation 180 minus 77. And that's going to be my 103. Vertical angles are congruent, so this is going to be 103 degrees. And again, two angles that form a straight line are going to add to 180. So I got 100 degrees here. This one has to be 80 in order to get us to that sum of 180. All right, so this one here, which is going to be different from all of them, 180 minus 100 is going to be 80 degrees. All right, so I found all that information. Now it's just a matter of determining what's the most useful of that information. Now, we don't need multiple things, multiple relationships up there to fit. All right, so as long as I can get one of them, you know, anything that ends with the conditional sentence saying, then they're parallel, is gonna be perfect. All right, so we're talking about the first four and the last one. All right. The last one would only come into play if it involved perpendicular, so I don't see 90 degrees anywhere. So we're going to leave that one off. We're going to focus on the first four because each one of them ends with the conclusion, then the lines are parallel. So I would ask myself, are the corresponding angles congruent? Are the alternate interior angles congruent? Are the alternate exterior angles congruent? Are the consecutive angles supplementary? The answer is yes. To which one? To all of them. Well, which one are we going to use? Whichever one you want. Because any one of them leads to the conclusion, then the lines are parallel. All right? So I'm looking at this and saying, okay, well, honestly, I just like saying alternate interior angles. So that's the one I'm going to go with. And most people like it because that's the nice Z relationship. You could see the Z. It's a friendly looking figure. It kind of stands out. Right? And so I can see that those two angles within that little cusp of, you know, in each part of the Z, they're both 77. So I know my alternate interior angles are congruent. So I know that line A is parallel, poor quality parallel symbol, to B because the alternate interior angles are congruent. All right, now that's actually, unfortunately, not the complete explanation. It's a way of kind of just shorthandedly justifying it. But there's a lot of details that were not included here. Because just because alternate interior angles are congruent does not necessarily mean that lines are parallel. There has to be two lines, or there have to be two lines, and there has to be a transversal involved. We've never stated, at any point, never stated any of that was in play. So what I'm going to write is really just a rule. If two lines are cut by a transversal so that the alternate interior angles are congruent, then the lines are parallel. Should be pretty close to what the rule says. It doesn't have to be word for word, as long as you get most of it.
That would be true for B and C because the alternate whatever interior angles are not.
Correct. So that would not be true for B and C. For all the same reasons that it is true for A and B. Right, now, again, you could have said corresponding angles instead of alternate interior. You could have said alternate exterior. There's a lot of different possibilities you could have used. I like alternate interior angles because we figured out all of them, so we're good to go. Now, they said determine which ones are parallel. They didn't ask us to determine which ones weren't. So I don't have to make any statement regarding line C, but if a question said, state which lines are parallel to which other lines and which ones are not, then I'd have to go a little bit further, but this is enough to justify it, all right? So really it's kind of a statement about what is the relationship and why it is, and also the geometric justification for that. Right, so it really is, it's kind of a hunt and peck kind of thing because you're going to be looking at a problem and then really just trying to find the rule or relationship that corresponds with that particular conclusion that you're trying to draw. All right, and most of the times, most of the time, it comes down to knowledge of the terminology. Will you get it? Absolutely, because there's even a place in here where we define what alternate interior angles are. But I kind of equate that to trying to have a conversation with somebody, but while you're having that conversation, you have to look up every single word that they're using while they're using it. It's like, well, that's not going to be much of a meaningful conversation. Right? So the more you try to internalize, the less you actually have to refer to, tables and definitions and things like that. It makes life a lot easier for everyone. All right, so like I said, we're just going to toss any problem, at least for now. I'll point out the ones that have meaningful algebra in it, but it kind of defeats the purpose, I think. So really it's just, and it'll save a couple of trees next semester, I guess. These trees are dead right now. Actually it's a small class, so it's fine. This problem is very similar, so I'm just going to put a star on it and tell you to tackle that one on your own. Because I think it's, as weird as it sounds, I think it's next class and then spring break, if I'm not mistaken. I'm pretty sure, yeah. So what I'd like to do is get